Hello children, in this session I am going to discuss about the topics of electric potential. This is our third section of electrostatics. I am going to cover electric potential in two sessions. So in this session I am going to start from the very first topic, that is electric or electrostatic potential difference. I think this term you already came to know in class 10th. But once again we are going to discuss the terminology. So what is electrostatic or electric potential difference? So for this I am going to consider 2 points, say A, another point is B. These 2 points are in an electric field. Now I am going to keep a test charge Q0. Obviously it is a unit positive test charge. I am going to place it at Q0. Now, if this test charge Q0 is moved from A to B, if I am going to move this test charge from A to B, the work done in moving this test charge from one point to another against the electrostatic force due to the electric field is termed as electrostatic potential difference. Once again I am going to explain the definition. What is electrostatic potential difference? Electrostatic potential difference between 2 points in an electric field is defined as the amount of work done in moving a unit positive test charge from one point to other against the electrostatic force due to the electric field. Mathematically, I am going to explain what is potential difference. Obviously, difference means 2 points are there. So, what is the potential at A? I am going to mark it as VA. What is potential at B? I am going to mark it as VB. Now, what is the difference I can write? Difference is VB minus VA. Potential difference is represented by VB minus VA, and it is equal to what we said. It is the work done on the test charge, that is Q0, in moving from A to B. And that becomes the mathematical form of electrostatic potential difference. Once again, what is VB? It is a potential at B. What is VA? It is a potential at A. So what is VB minus VA is the potential difference in moving the test charge from A to B. So mathematically it is the work done on the test charge Q0. Now what will be the unit of electrostatic potential difference? Basically electrostatic potential difference is a scalar quantity, and its unit we are going to measure in volts. We are going to measure in volts, and the symbol it is capital V. Now we are going to define what is 1 volt. You know how to define any unit values. The logic is very simple. I am going to use the formula. So as per the definition, the 2 points are A and B. If I am moving 1 coulomb of charge, so what about the equivalent work done? If it is 1 joule, then the potential difference is said to be 1 volt. So 1 volt can be written as 1 joule by 1 coulomb. So 1 V can be written as 1 J by C. So once again, what is the definition for 1 volt? The potential difference between 2 points is said to be 1 volt if 1 joule of work is done in moving 1 coulomb of charge from one point to other against the electrostatic force, and that becomes the definition for 1 volt. Now I am going to get into the second terminology, that is electrostatic potential. The second terminology is electrostatic potential. Now what is the only difference is potential difference is defined for 2 points, whereas potential I am going to define for a single point. So let us suppose that I am going to assume a point A where I want to define the electric potential. So what I am going to do, I am going to assume the other point is infinity. The other point is infinity. I am going to keep a test charge Q0 at infinity. Initially I am going to assume the test charge is kept at infinity. So what about if I am going to bring this test charge from infinity to that point, that work done gives a measure of electric potential. So once again, what is electrostatic or electric potential? Basically, it is the amount of work done in bringing a unit positive test charge from infinity to that point against the electrostatic force due to the electric field. There, what was electric potential difference? It was the amount of work done in moving a test charge from one point to another. Whereas electric potential at a point is defined as the amount of work done in bringing the test charge from infinity to that point. So obviously mathematically we can write what is the potential at A can be written as VA. Potential at A can be written as VA. Say if this point is B, I can write it as VB. So what is potential at B can be defined as the amount of work done on the test charge Q naught in bringing it from infinity to B. We marked it as B. So the formula becomes VB is equal to W infinity B by Q naught. So once again, what is electric or electrostatic potential at a point in an electric field? Once again, electric potential at a point in an electric field is defined as the amount of work done in bringing the test charge from infinity to that point against the electrostatic force due to the electric field, and that becomes a definition for electric potential. Similarly, it is also a scalar quantity, and I am going to define what is the unit of electric potential. The unit of electric potential, once again, it is volts, and I am going to give the symbol capital V. Once again, how to define 1 volt with this context? So what is 1 volt can be written as, once again, it is 1 joule by 1 coulomb. So how to define this? Once again, the electrostatic potential at a point is said to be 1 volt. Once again, the electrostatic potential or electric potential at a point is said to be 1 volt if 1 joule of work is done. If 1 joule of work is done in bringing a charge of 1 coulomb, from infinity to that point against the electrostatic force, and that becomes the definition of 1 volt. So these are the two important terms that we are going to use in our future topics. Now I'm going to get into the derivation for electric potential. So already we derived electric field due to a point charge. It was K Q by R square. I think you can have a recall, that is electric field due to a point charge is K Q by R square. Now I'm going to derive an expression for electric potential due to a point charge, and I'm going to get at the last, it will be K Q by R. What I'm going to get is K Q by R. So before getting into the derivation, what are the basic things we require while deriving the expression? Let us have a very quick recap. I'm going to have the expression for work done. You know, work done is F dot dl. You know this. I'm going to use while deriving the expression. In addition, what is the force on a charge in an electric field is F is QE. You know this. Next, what about the expression for electric field due to a point charge is 1 by 4 pi epsilon naught Q by R square. I think these formulas will help us while deriving the expression for electric potential due to a point charge. So let us start with the derivation. So I'm going to consider O is the origin in which I'm going to keep a charge plus Q. Obviously it is a source charge that creates the field. Now I'm going to consider a point A which is at a distance RA where the electric potential is to be determined. Once again, I'm going to consider a charge plus Q placed at the origin. Next, I'm going to consider a point A which is at a distance RA from the origin where the electric potential is to be determined. So what is the mathematical formula for potential at A? I think you know. Potential at A is VA can be written as W infinity A by Q naught. I think you can recall this. I'm going to mark it as equation number 1. Now, what is the definition for electric potential? We said is, it is the amount of work done in bringing a test charge from infinity to that point. So ultimately the potential can be measured by bringing a test charge that has to be kept at infinity and it has to be brought to A. That is the total case. But always we used to get a small work done, then we are going to integrate to get the total value. So let us suppose that at any instant the test charge is at P. I am going to assume actually the test charge has to be at infinity and it has to be brought to A. But in order to get a small value, what I'm going to assume, at any instant of time, the test charge Q naught is at P. Say that P is at a distance R from the origin where the test charge is placed. Now you say, since it's a positive charge, what happens to the test charge? You know that is F is equal to QE. This means this experiences a force Q naught E vector. Since it is positive, it will be outwards the point, away from the point. I'm going to mark it as Q naught E vector. Now, my aim is to bring the charge towards A. But what happens to the charge? The charge experiences away from A. So what I am going to do, I am going to apply a force equal and opposite to this. That is F vector is equal to minus Q naught E vector I am going to apply. And due to this force, let the charge suffers a very small displacement dl. Once again, let a force F vector acts on the test charge that displaces the charge through dl along the direction of A. So what is the force responsible is minus Q naught E vector. So ultimately this is a small work done. So what about the small work done? dw can be written as F vector dot dl vector. You know this. Now what is F vector? It is, I'm going to write it as minus Q naught E vector dot dl vector. Remove the dot, minus Q naught E dl cos, what is the angle between E and dl? Electric field is acting towards right, whereas the displacement is towards left. So what is the angle formed is 180 degree. So I'm writing it as cos 180. So what I'm going to get is dw is equal to minus Q naught E dl, because you know cos, obviously it will be plus 1 because cos 180 is minus 1. That minus 1 and minus leads to plus. So what I'm going to get is dw is equal to Q naught E dl. I'm going to mark it as equation number 2. Now, I'm going to do approximation. Let dl is equal to minus dr. Because we are supposed to represent the distance in terms of r, I can assume dl as dr. The negative sign indicates that it is opposite, the distance decreases towards the origin. To say the decreasing nature, we have put this negative sign. So I'm going to mark this as equation number 3. So what will be equation 2? Put 3 into. So dw is equal to minus Q naught E dr. Equation number 4. Once again, this is an important equation that we will use in some other expressions also. So please take care of this equation. dw is equal to minus Q naught E dr. Now, once again, what is this expression denoting? It is a small work done for a small displacement. But I want the total work done. From where? From infinity to A. So I can integrate this equation. So what about the total work done in moving the charge from infinity to A can be obtained by integrating with the limit infinity. What is the location of A? Is at Ra. It will be minus Q naught E dr. Next, you can put the value of electric field due to a point charge, that is infinity to Ra minus Q naught. What is E due to a point charges? 1 by 4 pi epsilon naught Q by R square dr. What are the things that can be taken out common? Sorry, it is to the out of the integration, that is minus Q naught by 4 pi epsilon naught can be taken out. So it will be infinity to Ra, and it will be 1 by R square dr can be written as R power minus 2 dr. So ultimately it is W infinity A is minus Q naught by 4 pi epsilon naught. It will be 1 by R, minus 1 by R to the limit infinity to Ra. I think you know R power minus 2 dr can be evaluated from x power n dx. That is x power n is x power n plus 1 by n plus 1. So it is W infinity A is equal to minus minus plus. So it becomes 1 by 4 pi epsilon naught Q naught by Ra. I'm going to mark it as equation number 5. That's all. So ultimately I'm going to put equation 5 in equation 1. So you say what happens? So what is potential at A can be written as, you know, Q naught will be cancelled off. So what is the thing that is left is 1 by 4 pi epsilon naught Q by Ra. In general, you drop the suffix a, the general expression will be V is equal to 1 by 4 pi epsilon naught Q by R. And that is the final expression for electric potential due to a point charge. Once again, I am going to explain the entire derivation. I am going to consider a charge plus Q placed at the origin. Number 2, consider a point A at a distance RA from the origin where the electric potential is to be determined. Next, in order to find the potential, what the definition says, the test charge has to be moved from infinity to A. So what will be the definition? VA is W infinity A by Q naught. I am going to mark it as equation number 1. Now, our aim is to bring the charge from infinity to A, but I am going to get the expression for small work done. So how to get it? So let at any instant the test charge is at P. I am going to assume the test charge is at P, which is at a distance R from the origin. I am going to keep the test charge at P. Now you say, what happens to the test charge? The test charge experiences a force, that is Q naught E towards right. But my aim is to bring the test charge towards A, so I am going to apply an equal and opposite force, that is F vector is equal to minus Q naught E vector, and due to this force, let the charge displaces through a very small value, say dl. So obviously there will be a small work done. I am going to start with small work done, dw is F dot dl. Now put the value of F. I am going to put F is minus Q naught E to be very clear. What is the value of F is not plus Q naught E, it is minus Q naught E dot dl. Remove the dot product, it will be cos 180. Why it is cos 180? Because the angle formed between E and dl, E is towards right, dl is towards left. So what is the angle traced is 180 degree. So I am going to mark it as Q naught E dl cos 180. You know cos 180 is minus 1, that minus and minus leads to plus. So ultimately I am going to get dw is plus Q naught E dl. Mark it as equation number 2. Now I am going to do a small approximation, that is let dl equal to minus dr. You know dl can be taken as dr. The negative sign indicates the decrease in the distance. Yeah, the charge is approaching towards the origin. For that nature we are going to put a negative sign. So putting it back, I am going to get dw is equal to minus Q naught E dr. So this is the expression for small work done for a small displacement, but I want the total work done in moving the charge from infinity to A. So I am going to integrate it with the limit infinity. A is at a distance RA, so the limit will be RA. I am going to put minus Q naught E dr. Put the value of E. E is 1 by 4 pi epsilon naught Q by R square. Take out the constants. R power minus 2 dr. When I am going to evaluate it, I am going to get 1 by 4 pi epsilon naught Q naught by RA. Put this equation in the first equation, Q naught gets cancelled, and I am going to get VA is 1 by 4 pi epsilon naught Q by RA. In general, drop the suffix, ultimately V is equal to K Q by R. This means V is inversely proportional to R. Here also the potential around a point charge is spherically symmetric. Yes, I am going to get into the next derivation. We are going to derive an expression for electric potential due to a system of charges. What we derived now is only due to a single point charge, and what was the expression? It is KQ by R. Now we are going to derive an expression for a system of point charges. Ultimately the location will be a single location. So I am going to assume a point P, say it is acted by number of point charges, say it is Q1, the distance of separation is R1. Similarly, this is my second point charge, say Q2, it is at a distance R2, say it continues. So what about the nth charges? Qn, the distance is Rn. Our aim is to get what is the total potential at P. So ultimately we are going to make algebraic sum of all the potential, that will be the result of total potential at P. So how to start? So what is the potential at P? Can be written as V1 plus V2, and it continues up to Vn. So what I can write for V1? V1 can be written as 1 by 4 pi epsilon naught Q1 by R1. Similarly, I can write it as V2 is 1 by 4 pi epsilon naught Q2 by R2, and it continues. What is the thing that is taken out? 1 by 4 pi epsilon naught can be taken out. So what about the common for the first one is Q1 by R1. For second, it is Q2 by R2, and it continues up to Qn by Rn. Can write in summation form. So what is V is 1 by 4 pi epsilon naught summation where I is equal to 1 to n. What are the repeating terms is q, so qi. R is also repeating, Ri. So where I takes the value from 1 to n. And this is the final expression for electric potential at P due to a system of charges. I think this expression is very simple. What you are supposed to do, you are supposed to add algebraically the individual potentials due to the individual charges, and that becomes the net potential at P. Now, I'm going to get into the third expression for electric potential. Obviously, it is the most important derivation that is usually coming in the board exams. So what is I'm going to derive is electric potential at any point due to an electric dipole. Electric potential at any point due to an electric dipole. You know what is an electric dipole? I think we derived expression for electric field due to a dipole also. Similarly, we are going to derive expressions for potential due to a dipole. But what is the location is, we are going to derive at any point. This means the point is not on the axial line. The point is not on the equatorial line. If I'm going to get up for any point, by putting some cases, we can get what is the value for axial and equatorial. So let us start. So what is the source? You know the source is a dipole. Source is a dipole. Dipole is AB. What about the charges? Minus Q plus Q. Midpoint is O. You know the two values are A. Next, number 2. I'm going to consider a point P. Let that point P makes an angle theta with the dipole at a distance r. Once again, this is my second consideration. I'm going to consider a point P where I want to know what is the electric potential. Where is point P? It is at an angle theta with the dipole, and it is at a distance r from the center. Now you know the potential at P will be due to minus Q as well as plus Q. So I'm going to write the contribution due to both charges. So it will be potential at P due to minus Q. I can write it as VA. Can be written as 1 by 4 pi epsilon naught Q by the distance is PA. I'm going to put a negative sign for charge because it is a scalar quantity and negative convention is a must. So once again, this is a very sensitive part. If it is minus Q, you are supposed to put minus Q. If it is plus Q, you are supposed to put plus Q. Yes, I'm going to mark it as equation number 1. Similarly, what is potential at P due to the charge plus Q? Can be written as VB. It's a positive charge, so I can write it as 1 by 4 pi epsilon naught Q by PB. Once again, PA, PB, they are equivalent to R in our derivation. So wherever it is R, not to put R, because you should know this distance is from the charge to the observation point. The distance is actually from the charge where you are observing to the observation point, and that distance is R. And here it is PA and here it is PB. I'm going to mark it as equation number 2. Now, what about the net potential? Can be written as V is equal to VA plus VB. What are the things that is taking common out? So I can write Q can be taken common, Q by 4 pi epsilon naught. So I'm going to turn it 1 by PB minus 1 by VA. I'm going to mark it as equation number 3. Now I think you have a very clear guess. What are the two unknowns? PA and PB. Geometrically, we are going to find PA and PB, put it back to get the final expression. So how to get PA and PB? So to get PA, I'm going to rub this. We are going to do a construction. You produce PO. You produce PO. After producing it, draw a perpendicular line AM. Draw a perpendicular line AM. Obviously, this angle is 90 degree. If this is theta, you know this is also theta. So what is the construction you did? You dropped AM perpendicular PO after producing it. After producing it. Second construction, to get PB, the same thing, we are going to draw a perpendicular line, say it is BN perpendicular to OP. BN perpendicular OP. So these are the two constructions we are going to do for getting PA and PB. So once again, how to get PA? Only we are going to do the approximation to get PA because it is not at all a right triangle. For that we have constructed a right triangle. Now, geometrically what I can assume, if the dipole is of small length, Pa is approximately equal to, once again this is the case when I am going to assume if the dipole is of small length, I can approximately make Pa is equal to Pm. I can make Pa is approximately equal to Pm, and you know Pm is Po plus Om. Pm can be written as Po plus Om. What is Po? Po is R. Om, I think Om you can easily get, since it is the base, I can write it as A cos theta. So Om will be A cos theta. So what is Pa we got is R plus A cos theta. Mark it as equation number 4. Similarly, not to do, directly I am writing Pb is R minus A cos theta. How you know this? From this right triangle, we are going to do the approximation. By the same approximation, I am getting Pb is equal to R minus A cos theta. So put it back. So it will be V is equal to 1 by 4 pi epsilon naught Q 1 by R minus A cos theta minus 1 by R plus A cos theta. Now, that is V is equal to 1 by 4 pi epsilon naught Q, you know it is R plus A cos theta minus R plus A cos theta by R square minus A square cos square theta. I think the simplification is very easy. For that I am proceeding in a quick way. So cancel off RR. A cos theta, it becomes 2A cos theta. So I can write 1 by 4 pi epsilon naught Q into 2A cos theta by R square minus A square cos square theta. So what is Q into 2A can be written as P. So what is the final form I am getting is V is equal to 1 by 4 pi epsilon naught. What is Q into 2A is P cos theta by R square minus A square cos square theta. And this is the final expression for electric potential at any point due to an electric dipole. I think once again I am going to repeat the entire derivation. We considered a dipole AB with charges minus Q and plus Q. The distance of separation is 2A. Consider a point P at a distance R making an angle theta where the potential is to be determined. Next, what is the potential at P due to minus Q is KQ by R, you know. So from that minus KQ by PA we wrote. Similarly, what about the potential at P due to plus Q? It will be KQ by PB. Once again, the net potential is their sum, that is V is equal to VA plus BB. By putting the values, I am getting is Q by 4 pi epsilon naught 1 by PB minus 1 by PA. So the two unknown are PB and PA that we obtained geometrically. For that we did two construction. We produced PO and we draw a perpendicular AM perpendicular PO after producing it. Number 2, similarly to get PB, we draw BN perpendicular PO. So what is the approximation we are saying? If the dipole is of small length, the length PA is approximately equal to PM. And Pm can be broken into Po plus Om, that is R plus A cos theta. In the same way, Pb can be obtained as R minus A cos theta. By putting it back, I am going to get the final expression to be V is equal to K P cos theta by R square minus A square cos square theta. With this, I am going to conclude today's session. Before concluding, I am going to put only one question to check our learning. So what is the question is, what is the electric potential at a point on axial line? And similarly, what is the electric potential at any point on the equatorial line? Once again, I can use this general expression to derive what is the value at axial line and what is at the equatorial line. So I am going to start for axial line case. So what is axial line? You know, axial line means obviously theta will be 0. Axial line of the dipole, if the point P is along the axial line, theta will be 0. So put theta equal to 0 in this equation. So what I am getting is V is equal to 1 by 4 pi epsilon naught P cos 0 by R square minus A square cos square 0. You know cos 0 is 1. So what is the thing that is going to left is 1 by 4 pi epsilon naught P by R square minus A square. This is the general form for axial line at any point. Now if I am going to assume if the dipole is of very small length, what I can write is V axial, you can neglect A from the denominator. Already in earlier cases also we did, when r is much greater than a can be neglected from the denominator. In that case I can get 1 by 4 pi epsilon naught p by r square. So when this equation I'm going to use is when r is much greater than a. Now what about the equatorial case? V equatorial, you know, theta will be 90. By putting 90, the equatorial value will be 0. Here theta is 90. So once again, there is an effective value of electric potential along the axial line, whereas no potential acts along the equatorial line. With this, I'm ending my session. Take care of yourself. Thank you.